Welcome to this video on Chapter 5.2 of AP Statistics, Experimental Design. We'll focus on this section on experimental design versus observational studies, which was dealt with more in the previous video. All right, so when we're designing experiments, we're going to call the things we do the experiment to the experimental units. And more often than not, they're people, and we call them subjects. If they are in fact people, and we are applying a treatment. So we're doing something to the experimental units or subjects that we're trying to measure a change in an outcome. And then our goal is to establish a causal link. So to prove the treatment we applied caused a change in the outcome. So we're trying to prove that cause and effect. One terminology that you should be familiar with is factors and levels of your experiment. So a factor are the variables you're interested in, such as one example could be gender and their alcohol preference. And so your factors are your gender and the alcohol preference. Levels are how much you can vary each of those factors. So gender, you could vary, we're just going to use the binary of male and female, or you could expand that to non-binary and have 3 levels. Alcohol, I just have 3 levels listed here, but there's more than 3 levels you could choose. Just an abstract example of factors and levels is, let's say you're experimenting on how to make the best cake. So you're going to first do temperature in the oven. So your levels are how much are the different temperatures you try. And then you're going to vary how much sugar. So your levels are the amount of sugar. Same thing with flour and eggs. And then you test how well probably the cake tastes, color, and whatever else you want to measure on the cake. There are 3 keys to experimental design. The first is control. And that is something to compare the treatment group to, so that you can say, hey, the group with the treatment reacted one way versus the group with the control. And with the most famous example people are familiar with is with medical treatments, experiments where you have a placebo, so somebody's getting a pill that doesn't have any active ingredients in it, and the treatment group is getting the pill with the active ingredients, and you compare them to see if the treatment group actually had a change. All right, so we have control, then we have replication. Now there's 2 ways replication is used in statistics. The case for experimental design is you want to do your experiment on more than one experimental unit, which hopefully is obvious that just one is not enough to measure your outcomes. So replication in terms of experimental design is just having multiple experimental units so that the variation within experimental units will average out and you will see the actual change that should be expected. The other use of the word is replication studies, which are important in science and statistics as well, where a group takes a study and tries to reproduce it. That is not what we're talking about here, but they are important in their own right, because even if you do everything right in an experiment, you can get weird results, you can get an outlier result. So you want to make sure that if you repeat the study, you get the same answers. They're valuable, but they're not as exciting as discovering something, so it's harder to get them to be financed and get grants for them. The third factor is randomization. So we want to randomly assign treatments, randomly assign groups, because while we're going to try our best not to be biased, we all have underlying biases, some we may not even be aware of. So you want to make sure that any variations in your experimental units get mixed between all the groups. So randomization does this the best, because you may not notice something that could affect your outcomes, and you assign all the people to one group and they all have this one factor. So you want to make randomization always your best bet. All right, some difficulties that happen with experiments is trying to group people by too many variables and overly putting yourself into the experiment. So randomization, again, best to do trying to match people by age, group, age, sex, smoker, non-smoker, physical activities, all that. Just do random, you'll get probably better results. All right, so we have a thing called randomized comparative experiments that I was just talking about, and we can show these set up in a chart, but let's go through first what's in a randomized comparative experiment. So you're randomizing two groups, and then you're going to apply a treatment or a control to one group, a treatment to another, or two different treatments. And then you're going to measure their outcomes and compare what your results were. And then the measured difference should just be due to the treatments that were applied. And there's a nice little diagram you can draw to display this. I have two different examples. One is with rats. So you randomly assigned 15 rats to each group and gave one a new diet and one a standard diet, and then you compared their weight gain. The other one is you randomly assigned 30 students to each group, and one group took a practice exam, the other group did not, and then you compare how they did on the actual exam. So notice that the first part is random, and then you have your treatment, and then you compare your results. All right, let's talk about some special cases. So one special case is blocking. That's just like stratification from sampling. It's just experiments, just a different word. So you're breaking people into groups based on a characteristic you think might affect your outcomes. So again, classic one is medicine. For the longest time, studies were only done on male subjects because they worried that female subjects, their hormones got in the way, which is kind of the point. So they finally realized we need to do it on males and females, so you want to block by gender so that you can see what difference different genders have on different medication. So that's the classic blocking example. Another example is with technology. If you were trying to test how easy it is to pick up some new technology you have, you might want to block by age because younger people might pick it up quicker than older people. Other things to block for: race can have an effect, especially in the medicine field as well. Economic status, depending on what you're measuring, might affect. So there's a myriad of things you can block, not just gender, but that's the most common one people think of. All right. Another special case of experimental design is match pairs design. And this is nice for taking out those underlying variables that could be affecting your results that you aren't aware of. So it's when you take two experimental units that are similar in all ways, and you get one has a treatment and then the other has control. One of the common ways to do this is just have somebody be their own match pairs. So let's say you were doing an experiment where you're trying to see which glove lasts the longest, like one is waterproofed and the other is not. You randomly assign left and right gloves to people, and they look exactly the same, just one has a treatment on it and the other doesn't. And then you measure how well the gloves lasted after a certain amount of time based on the difference in their wear, however you're going to measure the wear between the two people. the two hands, sorry. So match pairs is where you're splitting it up and then comparing two different individuals that are matched for a reason, or left hand, right hand matched for a reason. Another example that's on this slide is if you paired females with each other and males with each other, one person in each pair got a treatment group and the other person got a treatment group that were different. So one had weights, one had Pilates, and then you compared their whatever fitness measurement you wanted to compare. Here's an example, visual example, if you're a visual learner, of a match pairs design. So you have the tartar and control toothpaste and the regular toothpaste that 4 out of 5 dentists recommend. And you could do this either with people who have similar characteristics. I don't know how you would match it up wear-wise, teeth-wise, I don't know, measuring tartar on them. And you could match them up that way and have then measure the tartar buildup after a certain amount of time using the toothpaste. Or you could have randomly assign people to use the tartar control for a certain amount of time and the regular for a certain amount of time. And you could make it so that the person wouldn't tell the difference which one was tartar control, which one was regular. You just say, like, use toothpaste A for 10 weeks, use toothpaste B for another 10 weeks, and then you could compare the measurements of the tartar buildup. All right, so to summarize, experimental design, you want control to try to get rid of any of those lurking variables that might affect your outcomes that you don't want to measure. Replication, just make sure you got a lot of subjects or units that you are experimenting on. And randomize is the best way to go to assign groups. But you can block if you think there's a systematic thing that will affect your groups, your outcomes when you measure it. Our goal with experiments is to prove that something is statistically significant, and in later chapters you will learn how we figure that out mathematically to a certain degree and prove it to say that something is statistically significant. For right now, it's just, is there a big difference between the non-treatment and the treatment? Later on, there's a measurement we will do. And that is the end of the 5.2 video. I hope it helped, and I'll see you in the next video.